Hi, folks. This is Kevin Petrie. I run the research group at Eckerson Group. We're a boutique data and analytics research and consulting firm. Really pleased to have the opportunity today to speak with you, to join the Enterprise Data Summit and talk about an emerging discipline for data observability. I'll talk about what that is, why it matters, and then really dig into use cases. What are 10 problems that data teams can and should solve with data observability? Big topic. We're hearing more and more from practitioners within Eckerson Group's community about this, and I think it's more timely than ever, given what's going on. Concerns about data quality are very high, given the explosion in the usage and adoption of artificial intelligence. Similarly, concerns about cost are also high, given where we are in the economic cycle. So those are some of the themes that we'll be touching on here. So let's get started. If we want to frame this discussion, the pressure of modern data delivery is significant. And we work with, on the consulting side, a lot of leaders of data teams, of IT organizations that are struggling to align this booming supply of data in terms of volume, variety, velocity with a booming demand for data, looking at new users, including business-oriented users, looking at new types of applications that might be operational and they might include embedded analytical functions, and also looking at a proliferation of devices. So there's booming supply, booming demand. In between, data engineers, especially, and data teams are caught because they're trying to build the pipelines that will deliver the data to the right user at the right place in the right form. What can happen is that you have broken pipelines, bad data, busted budgets, and this is all caused by the reality of business, which is that your business needs change. Sources and targets continue to multiply. Data structures can evolve. Those drifting structures can start to break pipelines. Users, they make mistakes. These things happen and issues proliferate. So as a result, enterprise IT teams, data teams are struggling to deliver timely, accurate data to the business. I think we'd all agree that this is a significant problem. So data observability. The way we define this is to say that data observability is an emerging discipline. It includes two segments. The first is data quality. Data quality is looking at ensuring the timeliness, the accuracy of data, and it applies machine learning techniques to familiar methodologies for data quality. It studies the health of enterprise data to ensure that when analytics teams are receiving this data, they have what they need to generate accurate, trusted outputs. Data pipeline observability, meanwhile, is looking at the performance of pipelines, these workflows that ingest and transform data between sources and targets. And it's also looking at the performance of the infrastructure, cloud compute, storage, and so forth that's supporting those pipelines. Together, data quality observability and data pipeline observability help optimize that data delivery across enterprise environments, which increasingly today rely on distributed architectures. They might be hybrid, they might be multi-cloud, they might be all of the above. Those architectures need to support analytics and operations. Now, data observability also contributes to data ops initiatives, and I'll talk more about that include testing, CI/CD, continuous integration, continuous delivery, and orchestration of pipelines. So data observability is taking existing methodologies from APM, application performance management for pipeline observability, existing methodologies for data quality, and it's applying modern techniques and tools, including machine learning, to optimize modern data delivery. So I want to drill down briefly on data ops. Data ops is an area that at Eckerson Group we've done a lot of research on. Data observability is really the monitoring and intelligence foundation of data ops. Data ops includes testing, which is examining and validating both pipeline code and data quality. It includes CI/CD, so the continuous iteration of pipelines through branching and merging of pipeline code, similar as you would with other types of DevOps approaches for other types of software. It also includes orchestration, so automating the sequences of tasks, but also the workflows that are themselves sequences of tasks. And so that throughout the journey, the life cycle of data, you can have workflows that are starting to have clean handoffs from one another. That's critical because there are advanced applications that in a lot of cases are automatically consuming the outputs of data pipelines. So data observability, by drilling in and providing granular views of data quality, of data pipeline performance, can help with data ops. It can provide deeper root cause analysis when something goes wrong in terms of data quality, in terms of pipeline performance. It can provide deeper and broader KPI monitoring to improve testing. Data observability also can improve pipeline design, helping you plan ahead, understand interdependencies more fully, as an example, because you have better visibility into what's happened in the past. This can accelerate that branching and merging process of code that supports CI/CD for pipelines. If you can develop more reliable code, thanks to data observability, you can reduce the risk associated with workflow orchestration. You have higher confidence that a given workflow is going to perform as expected and meet reliability SLAs, and thereby have effective handoffs with other workflows. So data observability really helps data ops programs optimize data delivery. Okay, so I want to talk briefly before getting into use cases about the life cycle of data observability. I view this as having three essential phases, and what we show here applies equally to the notion of data quality and data pipeline performance. The first phase is validating and detecting. Here, we're studying patterns, we're studying breaks in patterns or anomalies, also understanding outlier values, failures in terms of delivery of data or execution of pipeline code, or errors. If you can validate those, if you can spot the problems, you can move to the next phase, which is assessing and predicting. Here, data teams are triaging issues, creating a stack rank of what they need to handle. They're measuring the impact. They're assessing the sensitivity of their workflows, of their data consumption to errors or issues that arise. They're also tracing workflows, so you can trace the chain of events that led up to an issue, starting to draw correlations between events that may or may not, on first blush, be related to one another. And through this, you can isolate root cause. So you can understand, why did I get null values in that column? You can understand, why did that pipeline fail to deliver the data that this machine learning model needs? Now we move into the third phase, resolving and preventing. So this is where data teams are controlling the environment. They're debugging. They've found a problem. They isolated a root cause. Now they're going back and fixing it. They're optimizing, for example, consumption of cloud compute resources, which can be a major source of sticker shock at the end of the month when organizations get their monthly bill from Amazon or Azure. They're also helping cleanse data to ensure that anomalies in terms of data values are reconciled, to ensure that the values represent reality. So data observability seeks to fix issues and improve uptime from an IT perspective and a business perspective, as well as decision quality, looking at the data scientists, the applications, the data analysts that are consuming data, and also cost. Okay, use cases. There are four categories of use cases. The first is preparation of your environment. This gets into infrastructure design, capacity planning, and pipeline design. The second category of use cases is operation. And here we're looking at performance tuning. We're looking at data quality, management of drifting data values or drifting data structures. And we're also in the adjustment phase, talking about optimizing resources that you're consuming, especially in a cloud environment, further optimizing by starting to tier your storage, spot that data that's most accessed, and also supporting migrations. So data teams can boost productivity and streamline infrastructure by addressing this. Another critical category of use cases kind of overarches everything, which is how do you fund this? What's the cost element? We're seeing a lot of interest in this, and I've done separate research on FinOps. That FinOps is an emerging discipline for predicting and measuring and reducing cloud-related costs. So if you do it right, if you address these use cases or a subset of them, business teams can have better uptime, lower risk, and higher value of data. They can thereby increase the upside of analytics and reduce the downside, because ultimately you want data to be an asset and not a liability. Let's dig in a little further to the first category of use cases, preparation. Enterprises need to prepare their environment for data delivery, for operating data pipelines. They need to design infrastructures based on a deeper understanding of performance and utilization trends. So a data engineer can huddle with a cloud ops engineer as he or she is designing a data pipeline to understand what the latency, throughput, utilization was associated with sets of cloud compute clusters that help ingest data, transform it, and then ultimately deliver it or expose it for consumption. There are a lot of ways in which the more you know about utilization trends, the more you know about performance trends, the better you can design your infrastructure and select the different elements of your infrastructure that are going to support the pipelines. The second here is capacity planning. Enterprises need to know how much capacity do I really need to support workload requirements on Black Friday, on Cyber Monday, at the end of the month to support financial reporting, at the end of the quarter to support reporting to Wall Street. What's the capacity required? Because it might well be you're operating on premises. It could also be that you're using cloud compute, but you need to have a real line of sight on what the cost of that. It's elastic, but elasticity can cut both ways in terms of cost. Workload simulations can help do this. You can help understand, for this given environment, I'm going to do a little test. I'm going to use a data observability tool, for example, from companies like Excel Data to simulate a workload. The third category here is designing pipelines based on data usage, KPI trends, and root cause analysis. So the first use case was designing the infrastructure that supports the pipelines. Now we're actually designing the pipelines themselves, figuring out what types of transformation scripts, what types of ingestion jobs are going to make the most sense for this environment based on understanding the KPI trends in the past, based on understanding root cause analysis of data issues or other things that arise in the past. So data observability can help data architects and also data engineers prepare that environment for optimal data delivery. All right, stage two, or I should say category two, operation. Now the data team is operating data pipelines across these oftentimes complex, diverse, distributed environments that might have one or more clouds, that might have some on-premise activity as well. Three big use cases that data observability can help with include performance tuning, data quality, and data drift. So in the first area, data teams can tune performance with alerts of issues that arise in terms of code quality, in terms of data quality. And if you have the right type of data observability platform, you could get automated alerts, but also automated recommendations about how to proactively resolve the issue that's arisen. Another aspect of operation, another use case is spotting and quick fixing data quality issues. We talked about machine learning driven anomaly detection. That helps quite a bit. And you can set threshold based alerts to generate scores of data quality and receive an alert when a data quality score, for example, when the consistency of data starts to fluctuate more than your tolerable band, or when a schema changes on a source, you can get alerts about these things. Another thing is data drift. And so data drift has a lot of elements to it: drifting values, drifting schemas, drifting elements of infrastructure metadata. But what we're talking about here is drifting values associated with the features, the data, the patterns that machine learning models need to spot. So if you train a machine learning model on consumption behavior for your shoppers last month, and then there's a big event this month, your consumers are going to change their behavior, and the data values are going to drift beyond what your machine learning model was trained to expect. You can spot that using a data observability, and you can then go back in and have your machine learning engineers intervene to pull the model out of production. The data science can retrain the machine learning model. So this is another way in which data observability is getting you that granular insight into what's really going into the behavior, the trends of your data. Data observability thereby enables cloud ops engineers, data and ML engineers to optimize data operations. All right, third big bucket, adjusting. Enterprises need to adjust their data environments as they go. There are a lot of ways in which this takes place. The big three use cases are optimizing resources to accommodate project changes. There are inevitably changes to an analytics project that will take place, especially in the area of data science. You might have data scientists that bring in a new external data set, a large data set that's going to enrich the ways in which they can train their models. That's great, but it's going to start to require new resources. Data observability can help you model what that's going to do to your infrastructure requirements, and you can start to optimize resources. It might well be that you have some spare on-premises servers that could handle model training off hours. That doesn't cost money as opposed to doing something prime time on the cloud. So there's a lot of different ways in which you can rebalance workloads and optimize resources if you have the right observability of workload behavior and what that means to system utilization. Second use case here is tiered storage. It's funny, I was at EMC for 9 years. I was there in the early 2000s and on up to 2014. In 2006 and 2007, we were talking about storage tiering. It still matters. What this means is that whether if you're looking at it in terms of block storage like we were or other things, you can start to understand which data sets are getting hit most. In a lot of cases, 10%, 5% of your data is getting most of the traffic, and the rest is kind of sitting there cold. You could probably put the cold stuff on cold storage, Glacier storage. You could put it on storage that costs less and doesn't require a lot of intensive support or costly support. Another point here, another use case is to assist migrations by discovering assets, automating the process for asset discovery, by modeling workloads on the target before you go. So data observability can help enable cloud ops engineers and data engineers to optimize resources, rebalance data, and guide their migrations. All right, final use case, and it's a big one. It's its category into itself, which is FinOps. Now, FinOps is not simply financial operations referring to handling transactions. Rather, this is in itself an emerging discipline that includes best practices, culture, and usage of automated tools to forecast and measure and account for cloud spending. Organizations have found that while there's a lot of flexibility moving to the cloud, there's also a real price tag associated with that. And those price tags, because they're usage-based and they apply to elastic resources, can be quite a surprise. They can be unpredictable and be higher than expected. Enterprises, especially in this economic climate, want to reduce that uncertainty and want to control cloud-related costs wherever they can. FinOps can help. It can help govern the cloud costs. So if you have a FinOps program, you can govern the cloud costs throughout the life cycle of a data project, throughout design, operation, and optimization of an analytics project, so that you're always aware of the implications of how you're consuming cloud resources, cloud application, cloud storage, cloud compute. Exclamation point there, cloud compute is very pricey, or can be, and network infrastructure as well. So what we find is that data observability assists these FinOps programs, because you can get visibility into how pipelines need cloud resources and consume cloud resources. You can better forecast and measure and account for that. Final note about FinOps is that it really is a collaborative process. It involves multiple stakeholders throughout the organization. It might involve a FinOps manager that serves as a liaison between a finance manager who gives the budget for a given project and IT. It can involve cloud ops engineers that are helping design and optimize cloud infrastructure. It can involve data analysts, data engineers, business analysts who are consuming outputs. And it can also involve, of course, data engineers that are helping design and manage those pipelines. All right, so I'll conclude here with some best practices, some observations, some recommendations about how best to enable and put in place a data observability program in order to identify and take advantage of these use cases. The first note is that you should treat your data observability program as a living, adaptable contributor to your business. As with all aspects of IT, this is not a set it and forget it approach. There is no single fix. Rather, this is going to be an incremental process by which you put in place a set of activities to optimize data quality, to optimize pipeline quality and performance. And I would recommend starting small, looking for a fixable problem that can be achieved in a near-term timeline. If you can get a quick win, you can build up the executive support, perhaps gain more funding to tackle bigger and bigger problems throughout your organization related to data quality and pipeline performance. This is a far better approach than ripping and replacing existing processes. A final point here is that you really need to prioritize those use cases. I think the 10 that we've walked through is a pretty comprehensive list. You want to prioritize those use cases according to business objectives. What does the business need this year, this 6-month period, and where are they experiencing the most pain? If you can address that, you can start to figure out how to deliver the value that you need with data observability. So if you take an agile, incremental, and business-centered approach to data observability, you can really help put the organization on a better track to efficient and effective data delivery. These themes here that I've talked about are also part of a report that was sponsored by Excel Data. Recommend checking it out if you want to learn more and get some granular examples of what these 10 use cases entail. Thank you very much. Happy to address questions.